Let's do another example. This one's just a little bit harder. This time A is a 3 by 3 matrix. We again want to find all the eigenvalues of A and then find a basis for the eigenspace associated with each of those eigenvalues. Okay, so again, our eigenvalues and eigenvectors satisfy this equation here, but that's equivalent to satisfying the equation A minus lambda I times vector x is equal to the 0 vector. So this homogeneous equation is what we're mostly going to work with. Now we want this homogeneous equation to have non-trivial solutions, so that means we want the determinant of the matrix to be 0. Otherwise, the matrix would be invertible and each column would have a leading entry for this square matrix. We wouldn't have any free variables. So in order for a square matrix to have free variables, to have columns without a leading entry, there must be a row of zeros once you get this thing into reduced row echelon form, which means that the matrix would be singular. The matrix is singular if and only if it's determinant is 0. So this is our characteristic equation. If we solve this, we will have our eigenvalues for the matrix. All right. So let's plug in. So matrix A is the matrix 0, 0, 0, 0, 1, 1, 0, negative 1, 1. And then minus lambda I. Matrix I is the identity matrix, just has 1s on the main diagonal, 0s everywhere else. If I multiply by the scalar lambda, I'll just have lambdas down the main diagonal, 0s everywhere else. Let's do the matrix-matrix subtraction. And I get negative lambda 0, 0, 0, 1 minus lambda 1, 0, negative 1, 1 minus lambda. Notice the matrix we're working with, it's almost the same as the original. It's just I'm subtracting every entry along the diagonal by lambda. Every other entry stays the same as the original matrix A. Right? All of these entries stay the same. All of these entries stay the same. The only difference is I take each entry down the main diagonal and I'm subtracting lambda from it. Okay? All right, so let's find the determinant. Let's expand along the first row. I'm going to have negative lambda times 1 minus lambda times 1 minus lambda, so that'll be 1 minus lambda squared minus 1 times negative 1, so that'll be minus a negative 1. Minus a negative means I'll be plus 1. And then the other entries along the first row are 0, so I'm not going to get any contribution there. 0 times anything is 0. Okay, I need to solve this. This is a polynomial again, but it's a little bit more intimidating, right? It's actually a degree 3 polynomial. If I take this, I get lambda squared if I FOIL it out, and then times another lambda, that's lambda cubed. For something like this, the best way to solve is by factoring. In this case, this is already a factor of the entire expression, right? So the idea here is I want to find a bunch of factors that multiply to 0. I already have something times something that multiply to 0, so I'm going to keep what I've got there. I'm going to leave this factored. I am going to try to work on this a little bit more. Okay, so I'm going to leave the negative lambda out. If I FOIL 1 minus lambda squared, multiply it out, I get lambda squared minus 2 lambda plus 1. And then I've got an extra plus 1 here. Okay. Now, ideally, we'd like to be able to factor this further. But if you think about it for a minute, this is not a quadratic expression that is easily factorable. I would need two numbers that multiply to 2 and add to -2. Well, the numbers that come to mind that multiply to 2, well, it has to be like 1 and 2, right? And I can't add or subtract 1 and 2 to get -2. 1 plus 2 is 3. 1 minus 2 is -1. There's no way I can get a 2 from that, okay? So this is not factorable any further, not easily anyway. So the strategy here is I'm going to kind of break it apart. I have two things multiplying each other to give me 0. So one way is if negative lambda is equal to 0, then lambda would just be 0. So if lambda is equal to 0, obviously this would work. The other way is if lambda squared minus 2 lambda plus 2 equals 0. This is a quadratic equation, and it's a quadratic equation that we cannot easily factor. But we do have a formula to solve quadratic equations. It's called the quadratic formula, right? And just as a reminder, for a formula like ax squared plus bx plus c equals 0, the solutions x to the quadratic equation are negative b plus or minus square root of b squared minus 4ac all over 2a. And at this point in your education, you are expected to have that memorized, okay? So in this equation, lambda is playing the role of x, right? It's playing the role of our variable. So let's plug into our quadratic equation. We have negative b. -2 is our b here, so negative b plus or minus the square root of our b squared minus 4 times a, which is 1, times c, which is 2, all over 2 times our a, which is 1. And so we get 2 plus or minus the square root of 4 minus 8 all over 2. So that's 2 plus or minus the square root of -4 over 2. Okay, we're almost there. Square root of -4. Now, normally we say we can't take the square root of a negative number, but when we're dealing with eigenvalues, when we're dealing with eigenvectors, we do think about imaginary numbers. The square root of -4 is the square root of 4 times the square root of -1, or I. So we are going to get an imaginary value there. And of course, the square root of 4 is 2, so I get 2 plus or minus 2i over 2. If I factor 2 out of the top, cancel with the bottom, I would be left with 1 plus or minus 1i. And so I get 3 eigenvalues. Lambda equals 0, lambda equals 1 plus I, lambda equals 1 minus I. Okay? All right, we've got our eigenvalues. Next, we need to find an eigenspace associated with each eigenvalue. So what we're going to do is we're going to take each one of our eigenvalues in turn, we're going to plug it back into this equation, and then we are going to solve the equation. Okay, the solution to the equation for each of our eigenvalues, that's going to be the set of all eigenvectors associated with that eigenvalue. And then we can use the solution to find a basis for that eigenspace. All right, so let's do it one at a time. Let's start with the easy one, the one that's not so scary, lambda equals 0. So let's look at lambda equals 0. So that's going to be a minus 0 times I times vector x equals 0. Okay. Now, of course, 0 times I is just 0. So I'm just going to get a here. Right? So matrix A, what was that again? 0, 0, 0, 0, 1, 1, 0, -1, 1 times vector x equals vector 0. So I want to find the reduced row echelon form of this. Okay? solve the system. Row 1, row 2, row 3, plugging it into our calculator. And so the reduced row echelon form is this matrix here. And so I get 0, 1, 0, 0, 0, 1, 0, 0, 0. And we can see that there is a column without a leading entry. Column 1 does not have a leading entry, which means it's going to be associated with a free variable. Okay, so solving the homogeneous system, imagine having zeros in the augmented part here. Okay, solving the homogeneous system, I'm going to get x1 equal to a free variable. The first row tells me x2 equals 0. And the second row, as an equation, would be 0x1 plus 0x2 plus 1x3 equals 0. So x3 equals 0. And so I get the solution, x1, x2, x3 equals t times 1, 0, 0. So my eigenspace for 0, S sub 0, my eigenspace for 0, is going to be the set of all vectors that look like this. All vectors of this form are going to be an eigenvector for the matrix with associated eigenvalue 0. Okay? So the span of vector 1, 0, 0 is the eigenspace, and 1, 0, 0 is a basis for that eigenspace. Okay. All right. Let's do our next eigenvalue. Here's where it gets a little more interesting. We get 1 plus I. Let's get our eigenvalue 1 plus I. So now we want to look at the homogeneous system. A minus 1 plus I in place of lambda times the identity matrix. We'll multiply that by vector x. We want to know when we get the 0 vector. For what values of x do we get the 0 vector? Okay? So matrix A is the matrix 0, 0, 0, 0, 1, 1, 0, negative 1, 1. And then scalar times I, we'll just have that scalar down the main diagonal. And so we get, after the subtraction, we will get negative 1 minus I, 0, 0, 0. 1 minus 1 plus I is going to be negative I. 1, 0, negative 1. And then 1 minus 1 plus I is again negative I. To solve the system, we need to get this into reduced row echelon form, this matrix here into reduced row echelon form. So again, we're going to go to our calculator. Now, this matrix has complex numbers in them, imaginary numbers. We can actually input imaginary numbers in here, though it's a little bit different than how we write it, okay? So Python actually uses the engineering convention. Engineers use the letter J for imaginary numbers. So we're going to use the letter J when we put it into our calculator. Right? So negative 1 minus, and another thing, you cannot just put a J. It has to be a coefficient in front of that J. So negative 1 minus the imaginary number, so it'd be negative 1 minus 1 times the imaginary number for that first entry. Okay? 0, 0. Second row, 0, -1 times the imaginary number, 1, and then 0, -1, and then -1 times the imaginary number. Let's make sure we get the correct matrix here. There we go. So if we run that, there we go. We have our matrix in reduced row echelon form. 1, 0, 0, 0, 1, and then we have 1i, 1 times the imaginary number I. So just I. 0, 0, 0. Okay, so let's write that out. We have 1, 0, 0, 0, 1, the imaginary number I, 0, 0, 0. Okay, so this is in reduced row echelon form. Notice we do have a free variable. Our last variable, x3, does not have a leading entry in this column, so we will have a free variable. So if we throw in the augmented zeros, we can use this to solve the homogeneous system. We know we will have a free variable x3. Let's use row 2 to get us x2. That's 1x2 plus I times x3 equals 0. x3 is our free variable, though, so let's swap out x3 for our free variable t. And we see that x2 is going to be -it. Notice we're doing the math the same way as we always are. It's a little scary because we have these imaginary numbers that we don't usually deal with, but for the most part, the math just works out the same. Okay, you do the math the same way. Row 1 will tell me about x1, and I get x1 plus 0x2 plus 0x3 equals 0. Okay, so I know what x1, x2, and x3 are in terms of the free variable t. And I get 0, -I, 1 as the vector here that I'm going to scale by multiplying t. Okay, any vector of this form is going to be an eigenvector associated with the eigenvalue 1 plus I. Okay, and so our eigenspace for the eigenvalue 1 plus I is the span of the vector 0, -I1. And the basis, which is the answer we're really looking for, one option for the basis is vector 0, -I1. All right? Okay, we've got one more eigenvalue to work out. We need to find the eigenspace associated with the eigenvalue 1 minus I. I'll move a little faster here since we've already seen this twice. So lambda equals 1 minus I. Plug it in for lambda in the homogeneous equation. Matrix A is still 0, 0, 0, 0, 1, 1, 0, -1, 1. And I'm going to subtract 1 minus I times the identity matrix. That just gives me 1 minus I down the main diagonal, 0 everywhere else. Do the matrix subtraction, I get -1 plus I, 0, 0, 0, 1 minus 1 minus I. It's going to be a positive I. Don't forget to distribute that negative, right? 1 minus, and then we subtract all of 1 minus I. So that negative distributes in here. I'll get -1 plus I if I distribute the negative. And that's why this I is positive. 1, 0, negative 1, and then positive I again. 1 minus I is positive I. To solve this homogeneous system, I want to find the reducer echelon form of my coefficient matrix. So let's do this one more time. Let's call my matrix here C. So I get negative 1 plus 1j. Make sure you translate it correctly so that it will work in the calculator. Row 2 is 0, 1j, 1. 0, negative 1, 1j. Find the reducer echelon form of my new matrix C. And we get 1, 0, 0, 0, 1, negative I, negative 1i, 0, 0, 0. One, 0, 0, 0, 1, negative I, 0, 0, 0. Okay. X3 is again a free variable. Let's call X3t. Row 2 will give me my equation for X2. So 1x2 minus ix3, which is free variable t, equals 0, which means x2 is equal to it. And then looking at row 1, x1 equals 0. So the general solution of this homogeneous system is t times the vector 0, I, 1, which means this vector is a basis for the span. The eigenspace for eigenvalue 1 minus I, and I just wanted to double check that that is the eigenvalue, it is the span of 0, I, 1, and the basis for this eigenspace, which is what the problem was really asking for, is this vector right here, 0, I, 1. And we found the eigenvalues and a basis for the eigenspace for each eigenvalue for this matrix.